Here I will review the boundary conditions that we need to put on our model. At every point on the boundary, the traction or displacement has to be defined, and this is true of normal as well as two tangential directions. So this is, what we have seen before. Let's take a look at the displacement or essential boundary conditions first, and then we'll take a look at the traction or natural boundary conditions. You get an essential boundary condition from the symmetry due to periodicity. So that's one of the symmetry surfaces where we cut the model, where the symmetry plane cuts the model. And then the back plane is also a symmetry plane, and that's shown over here. And on the symmetry plane, you basically have normal displacement is 0, and tangential traction in two perpendicular directions is 0. So it's similar to what ANSYS calls frictionless. And then you also have a displacement or essential boundary condition at the top of the mid-nozzle, and there you have again a frictionless support, and frictionless is an ANSYS terminology. And again, the normal displacement is 0 and the tangential traction is 0. And that boundary condition approximates a connection to the upper nozzle. So, this part is actually connected to the upper nozzle, which we are not modeling over here. So this boundary condition approximates that connection. Those are the displacement boundary conditions. Let's talk about traction or natural boundary conditions on the model. You have a normal traction due to pressure from the propellant. So you have, hot gas flowing through the nozzle, and this boundary condition models the pressure due to that. This is calculated using 1D gas dynamics, and Mr. Andy Sadhwani, he lays out, the process by which he made these calculations, and we'll also provide you with the Excel file containing his calculations. And we apply a pressure that varies in the axial direction, so it's going to vary in this direction. It's not going to be a constant pressure. And we're also going to apply a force from the regeneration channels, or the regenerative cooling channels, which are, because of the pressure in those channels, which you don't model, but they tend to pull the joint apart, and those forces are modeled here. So we'll just put the force on, on the surfaces over here. We won't model the channels itself, but we'll model the separation forces coming due to those the pressure in those regenerative cooling channels. And again, Mr. Andy Sadhwani talks about that, and we'll get to that later. Then there's also traction at the contact surfaces where the parts are going to come into contact. But we don't know a priori where the parts are going to come into contact, and that's a big complication. So this is the undeformed model, and that's the deformed model, and this is exaggerated. It's almost like it's opening its mouth. and you can see that, now in the deformed model, the traction on this surface and this surface is 0 because they are not in contact anymore. But over here, the part is in contact. The parts are in contact, and so you have, a traction, and which means that the traction becomes dependent on the displacement. Okay, instead of knowing, instead of having a known value of the traction, you have a traction that's dependent on the displacement. And this is highly nonlinear because also it can go from 0 to a finite value and so on, and that brings in a real nonlinear complication into the model, and we'll see how that changes the finite element solution procedure. And then all the other boundaries, the default is 0 traction in the normal as well as tangential direction.